and welcome to September's BTS evening presentation. Tonight's lecture is on dewatering strategies for underground infrastructure in the London Basin. And this evening, our speaker is Dr. Toby Roberts, Chairman of WJ Group. Toby Roberts is an expert in the design and implementation of groundwater control systems for large excavations, foundations and tunnels with extensive contract experience in Europe, the Middle East and Canada. Toby is a founder member and current chairman of the international dewatering contractor WJ. He has authored and co-authored more than 40 publications on construction dewatering, including Syria C750 in 2016, the UK Best Practice Guide for Construction Dewatering. Toby is also a Fellow of the Royal Academy of Engineers, a Chartered Civil Engineer and a Chartered Geologist. Welcome this evening, Toby.
Thank you. So this evening, I'm going to walk you through the range of strategies used to manage groundwater for underground construction in the London Basin. I'll start by looking at the setting for projects in the London Basin, and then we're going to drill down through the strata, looking at a succession of projects and strategies. This picture shows some of my staff installing a well out of the roof of a tunnel, which is not something you see every day, and I'll be looking at why you might want to do this. So first of all, let's just look at the settings. The geotechnical profile is probably the most important. Well known since Victorian times, London sits in a basin with chalk at the bottom and a succession of soils above. Early tunnels were either cut and cover or driven open face in the London clay. The chalk and the profile above rises to the east, with the superficial soils progressively eroded. The chalk is a major water supply aquifer and is recharged at outcrop to the north and south of London. The pore water pressure profile is complex, and we'll look into the reasons for this in a moment. So we've got, apart from the geotechnical profile, the hydro-geological conditions, we've also got the structures that we're building. These may be excavations, they may have cut-offs, they may be shafts, headings. TBM tunnels can typically be driven in water-bearing ground, so we're not really looking at those. And we need to usually think about instability due to inflow of groundwater, but also where we have pressures in strata below us, we have to consider uplift pressures. And then we have to consider the context that we're in. What are the surface access conditions? Are there any environmental concerns? What options do we have for discharging the groundwater? Is there access to a river, or are we discharging to sewer, or are we very constrained on our discharge? Is there any treatment needed for the water that we're pumping? To what extent are we concerned about the neighbours, and is there a settlement risk associated with the dewatering? These are all the factors that have to be considered in the strategy. So looking at the hydrogeological setting in a bit more detail, this is a set of data from central London, from Crossrail. So I'm afraid we've got a mixture here. So down the side, we've got meters tunnel datum, with 100 being sea level, and 105, 110 typical ground level. And then we've got pore pressure along the top. You can see the profile on the right there, the River Terrace deposits, the Upper Aquifer, the London clay, the Lambeth Group sands, and then the Thanet Sand and the chalk. And we tend to divide those into upper, intermediate, and lower aquifer. The little individual dots there essentially are individual piezometer readings. So the ground profile, or the hydrostatic profile, was probably hydrostatic up to about 1830. That's the dotted red line. The lower aquifer was overexploited for water supply between about 1830 and about 1950. That led to a big drop in the water level in the chalk. Centres on Trafalgar Square. It got down to about 70 metres below ground level, with a cone of depression going out from there. Since then, the groundwater levels have risen, and this, which is mainly from the City of London, around at about 75 metres tunnel datum. And you can see the intermediate aquifer there, the channel sands in the Lambeth Group, have an intermediate pore water pressure profile. So it's not fully draining with the chalk, and it still maintains some pressure. So this is a chart that I originally prepared for my PhD 40 years ago, and it's been updated, and this is the version from the current Syria C750 best practice guide for dewatering. And essentially it's a plot of drawdown down the left-hand scale, so the amount by which we want to lower the water table, and permeability along the bottom, going from 10 to the minus 8, virtually impermeable clay, to 10 to the minus 1, a more or less infinitely permeable gravel. And it indicates, these are the two parameters which control the selection of your method of dewatering, and it indicates what sort of ranges they might work in. If we overlay onto that the sort of range of conditions in the various strata in London, we can see that we cover pretty much the whole area that dewatering is feasible, with river terrace gravels at a shallow level. Then we have the London clay, which is impermeable, but then we have the Lambeth Group channel sands with a big range of permeabilities, and then the Thanet Sand, and then often more permeable chalk below that. So it's this whole range of conditions that makes dewatering in the London Basin both endlessly fascinating and a real challenge. And don't forget, we're also dealing with 3 completely different aquifers. The parameter which is probably least understood by those who are not looking at this every day is the role of boundary conditions. So the river terrace gravels at the top, I mean, there's some link to the river, and otherwise links to the, probably links to the sewer, which sewers and leaking water mains that control the water level. The Lambeth Group channel sands below the London clay, the intermediate aquifer, has relatively low transmissivity. Transmissivity is what hydrogeologists use. It's the permeability times the thickness. It's an indication of how much water might flow through the aquifer. The channel sands are bounded above and below by clay, and the lateral recharge is limited and probably quite distant. So we have potential for large distance of influence and relatively limited inflow. The Thanet Sand is quite similar, relatively low transmissivity. It's part of the lower aquifer. It's got a barrier boundary above, formed by the Lambeth Group clays, but it's got a recharge boundary below from the chalk, because they're hydraulically linked. So the recharge is significant and very close, which means potential for very rapid recoveries if you interrupt the pumping. So you get a limited distance of influence, and the flow and the well yield is limited by low permeability. And then below that, we have the chalk aquifer. So this is a major aquifer. The water flows in the fissures. It's potential for medium to high transmissivity. It underdrains the Thanet Sand above. generally limited recharge from below because it's quite anisotropic, and the recharge is distant because it's from the edge of the London Basin. So we have potential for large distance of influence, high flows, and high well yields. And note the use of the term potential, because it very much depends on the jointing of the chalk. Because where there's no jointing, there's actually minimal permeability and minimal flow. This is a limited edition print by the artist Stephen Walter, in which he set out to map as much as possible of what is under London. So railway tunnels, pedestrian tunnels, road tunnels, sewers, water mains, power tunnels, government tunnels, basements, post office railways, redundant tunnels. There are no surface structures marked on this map, and yet it's a recognisable map of London. And that's because many of the tunnels follow the road and the railway network. That's my experience, which this talk is based on. And that's just a list of the some of the projects of the photos that I'm going to be using in the course of the presentation. They're not all captioned, so you may be able to recognize them if it was your project. If you zoom into Stephen Walter's map, you find that there is incredible detail about these underground structures. A lot of it is historical, but you can see there the tideway tunnels are marked. So he was prepared this in 2012, so he had some confidence. I haven't actually checked if the HS2 tunnels are on there. Stephen Walter's website includes a zoom tool, so you can actually zoom around and move around this yourself. Okay, so now we're going to start looking at strategies, and we're going to start at the top in the terrace gravel. So this is a photograph of the Heathrow Terminal 5 works, taken in about 2002. And we can see there water-bearing terrace gravels, which in this case are dry, and the excavation is into the London clay. There's no significant flow coming from the terrace gravels at the interface, and there's not a dewatering well in sight. So how was that actually achieved? Well, Heathrow Terminal 5 is built on the site of a former Thames water sewage treatment works and sludge drying beds. And it turned out that those had a historic slurry cutoff, that's the black line, that ran round most of the area of the development. And that provided a cutoff into the London clay. So following a review, the strategy was to extend that cutoff so it completely encapsulated all of the deep excavations for Terminal 5. So in effect, you had this, we had the sort of existing conditions, a lot of made ground, terrace gravels and London clay, removed the overburden, checked that the existing cutoff was there and looked okay, installed additional cutoffs to complete it, then trench excavations to drain the terrace gravel, and then once we get into the chalk, a toe drain and excavations in the clay. So it looked like this in reality, in the snow. It's just trenching with a sump pump, pumping the water and steadily pumping that out into a discharge pond. The discharge pond was actually covered in little plastic balls to make it less attractive to birds, which of course they didn't want in the middle of the runways while the development was going on. So cutting off the terrace gravels is certainly a good and effective strategy. There are circumstances where a cut-off isn't feasible. So this was the case for the redevelopment of the television centre in White City. This has a listed facade that had to be retained. They wanted to deepen the internal basement. There was limited sewer capacity, and they couldn't put a complete cut-off around the structure because of the bits of it that was protected. So the strategy was to put in as much of a cut-off as they could, use deep wells, we can see in the photograph there, and then discharge to recharge wells. So in section, that looked like this, the recharge wells in green, and these were both as a means of disposal and to maintain external groundwater levels. And the sheet piles didn't go around the full perimeter, so we had plenty of leakage, and then we had abstraction wells on the inside. And it's worth noting here that recharge is an increasingly important part of the dewatering world for several reasons. It's an alternative means of disposal, avoiding the cost of sewer discharge or the consents required for discharge to surface waters. In the right circumstances, it can provide mitigation for surface settlement, risk to neighbouring structures, as was the case here. And importantly, it is also recognised by the EA as a mitigation measure, which can subject the whole of the dewatering scheme to an exemption from licensing. So it's something that we increasingly look at as an option. And that's what it looked like in plan. You can see the circular television centre building. Plot A and C had the deepened basements. We had sheet piles around one side, and then on the internal side we had the deep wells, and then the recharge wells outside the sheet piles and over towards the site perimeter where there was concern about adjacent structures. So there are other circumstances where we can't get a full cut-off, and that's if the clay isn't present. And this occurs certainly in the east of London, where the London clay and the Lambeth Group have been eroded away. And here we're looking at one of the tideway CSOs at Deptford Church Street. So we've got an excavation in the River Terrace deposits, secant piles down into the Thanet Sand, and we need to dewater effectively the Thanet Sands to control the inflow under the secant piles. We need to check that there isn't a risk from uplift from the chalk, and that was sufficiently deep for that not to be a problem in this case. So we can see there the excavation down to full depth, just above the Thanet Sand. And we did modelling before we started to investigate the likely range of flows. The actual range of flows was sort of 3 to 5 litres per second, and that fell well within the model range of 1 to 12. So below the terrace gravel, we get to the London clay. And of course, the London clay is relatively stable, certainly in the short term during construction. So why might we consider dewatering? We can't control the pore pressures in London clay in any sensible time frame, but sometimes pressure relief is needed in the strata below to control uplift pressures. And this was the case for the auxiliary shaft at Crossrail at Limo, at the Limo Peninsula. We'll actually be looking at the main drive shaft later on. That was a bit deeper. So it's a 27-metre diameter by 40-metre deep shaft, founded in the London clay about 5 metres above the Lambeth Group. And the strategy here was to install 9-number passive relief wells, So these leak the excess pressure into the excavation where it's removed by sump pumping. There's about 30 metres head in the channel sands, and the flow that we were dealing with was just a couple of litres per second, so minimal. So passive relief wells can work well in the right setting, but note, the site team is often surprised that water flows from the wells. So that hadn't been explained to them, but that is, of course, essential. So this doesn't work well if the flows are at all significant. It's important that they're low. Also, there's an option to test pump in advance of the excavation. So that can be good because you can confirm what the flow rates are going to be. If the target drawdown is going to be below dig level, then you can't get a passive relief system to work. It has to be pumped. And finally, although this is passive relief, the EA, Environmental Agency, consents apply unless they're subject to some kind of an exemption, possibly due to low flow or if the water is recharged. So that can be an effective method for excavations in the London clay with a high pressure below. Below the London clay, we come to the Lambeth Group. This photo is from the last advance for Tideway Kirtland Street TBM launch chamber addit. Dewatering was by a combination of surface wells and tunnel well points, which you can actually just see through the SCL lining at the top there. And we're just getting away with it. The sand layer's dry, but there's a sort of silt clay layer below, which is a bit marginal. I think the expectation was that it would be more clay than silt. So it was marginally stable, but I think we got away with it, and that last invert was cast. It's an important point to note about the Lambeth Group is that it is predominantly cohesive, and at some locations it's entirely cohesive, but it contains occasional channel sands in it. It has a series of characteristic layers that the geologist can identify, varies in thickness from 5 to 20 meters, and these granular horizons are quite variable. They may be laminations, they may be channels. I've come across them from as little as a couple of meters to up to 300 meters wide, and perhaps they're greater in some places. And often they're channel features, so they probably have one long dimension. And of course, on a project scale, you never quite know what that might be, but I guess it might be substantial. And they may vary from a few millimeters to 12 meters. This photograph of a fay shows a channel sand layer that's been dewatered with well points. And in the middle is what's known as the Mid-Lambeth hiatus, which is a marker band, relatively easily identified. And in central London, at least, that is the hydraulic divide between the intermediate aquifer and the lower aquifer. So typically sand in the Lambeth Group below the Mid-Lambeth hiatus drains with the Thanet Sand. So now we'll look at a project. This is the first bit of infrastructure constructed for Crossrail, actually constructed in 2004. It was the vent shaft under the Moor House development in the city next to Moorgate. And there's a couple of papers on it by Morrison and McNamara. So it's a 10-meter diameter, 38-meter deep shaft. It was constructed after completion of the superstructure to minimize program implications. So the piles were installed before the shaft, and they were sleeved down to -25 so that the subsequent tunnelling and Moorgate station works wouldn't impact on the building. So it was constructed from the second basement level by underpinning. Wet construction was not viable due to the difficulty of dealing with wet spoil in the City of London. And the shaft was founded through the London clay, through most of the Lambeth Group to just above the Thanet Sand. And you can see the water levels there above the dig level. So we needed to control the pore pressures in the Thanet Sand layers and take the water level in the Thanet Sand down a few meters to below dig level. So the dewatering scheme essentially was a ring of ejector wells and deep wells at about 3 meter spacing. And then we had 3 strings of piezometers. So each string had an instrument in each of the layers. We had restricted access, so we finished up with some of the wells inclined so that we could get an even ring around the perimeter. So in section, you can see there we had inclined wells. So the wells are inclined so that we can, we don't want the wells to be too close to the face. We actually want to be a few meters back. If we're too close to the face, we risk exposing the screen and then we lose the vacuum and lose the performance of the system. The target water pressure in the Lambeth Group was 0 kPa, and there was obviously great concern about affecting the active length of the piles and the skin friction on the piles, which were in quite close proximity. And we use ejectors because they provide vacuum assisted drainage. So there were some challenges on the installation. We were drilling inside the atrium, but all the fit out work was going on above. So we were drilling incline through 2 basement levels with restricted headroom, and the drilling returns came into the 2nd basement with the rig up on the ground floor. And then wells was actually installed in the 2nd basement. There was actually benefit later on because the shaft was constructed from ground floor level while all the dewatering system was in the 2nd basement, so it was protected from damage during construction. So that's the exposed Lambeth Group face. So you can see the sand, it was dry. You can just see Andy McNamara showing his face, slightly younger in the left there. So the flow was just 3.5 litres per second, mostly from the Thanet, and the piezometers in the Lambeth Group actually indicated negative pore water pressure. And we had a contingency option for in-shaft well points, which on the day wasn't required. Had they been required, then the system might have looked something like this. This is a well point system installed in the tideway shaft at Heathwall. So surface wells used to get the bulk of the drawdown, and then these shaft well points installed after partial excavation in order to tackle the interface and get the water level right down at the interface so the SCL lining and excavation could extend back below and into the Lambeth Group. So basically there is this dilemma. Should we be using surface systems or should we be using in-tunnel or in-shaft systems? So surface systems, well, there's limited access, particularly in a congested urban area. If the sand layer is intermittent, are we actually going to hit it, or is our well wasted? It's quite inefficient to install a long well, but it only has a short well screen. And we need to be using ejectors or submersible pumps. One benefit is we're unlikely to be drilling in artesian conditions. In tunnel, better access because we're much closer to the target layer. We can use systematic drilling to identify the presence and extent of the sand. Cost effective at close spacing. We're relatively short wells. A simple and robust vacuum system providing the drawdown is modest. But we may be drilling into artesian conditions, and that requires a stuffing box. So combined approach, particularly where the pore pressures are high, is often the most attractive strategy. So, to some extent, through my career, we've been going through a 30-year journey, initially using uh, surface equipment below ground, uh, but on things like the Jubilee Line extension and the HS1 tunnels coming through North London and the Docklands Light Railway. But then more recently, Crossrail in Toronto, where actually conditions have some similarities to London, and on the tideway tunnels, we now have specialist below ground equipment, which is compact and smaller. And actually now we're beginning to find that a lot of surface sites are quite congested and constrained. So we're now starting to use in-tunnel equipment for surface installations where we can't get access. So this is an example of an in-tunnel only installation at Farringdon. The TBM tunnel acted as a pilot tunnel, and where there was a channel sand layer pretty much at axis level. So we've got well points installed almost horizontally to target the sand layer and the interface. The TBM tunnel in this case was blind because there was an adjacent contract. So we had to pass the pumping line through the advancing face, which was a bit of a challenge. And these well points get lost as the face advances. And occasionally it was necessary to install replacement well points to keep the pressures down behind the advancements. And we had two tunnels here, so we were sometimes able to drill cross links or use the dewatering from one tunnel to dewater the other, or connect pumping systems across to adjacent tunnels, make our life simpler. Because the Lambeth Group sand horizons are intermittent, we're often probe drilling, so that's auger drilling as part of the dewatering strategy. This may be just proving that there's enough clay cover, or defining the extent of a known sand channel. So in this case, yes, we're just confirming the conditions, and you can see the opening sets there for a cross passage. I think this was on one of the cross passages on Crossrail. But of course, where there's a risk that you encounter sand under pressure, then you need a strategy, because you're just going to get an inflow of water and an inflow of sand. And usually you need to be drilling through a valve bolted to the tunnel lining and a stuffing box so that you can close anything down that you find. And this is effective up to about 2 bar pressure. Installing wells into a pressurized sand layer is not straightforward, and this impacts on productivity. Minimizing the need to be installing artesian wells is usually part of the dewatering strategy. And we have sort of nimble, powerful, compact drill rigs to get into tight spaces, and increasingly those are looking to be electric rigs, which have a lot of advantages, certainly in the tunnel environment. So this is another in-tunnel scheme. This is actually the Morehouse shaft. So this is on the right here. You can see the shaft that we described the construction of just earlier. And then about 10 years later, we were back and the tunnels and the box had been installed, and VD5 had been installed, and these are the TBM drives. And we were involved then in the construction of VD4 that linked into the shaft. No chance at all of surface access for this. And actually no access into the westbound TBM just above. So this was quite a sort of three-dimensional problem. We were installing wells from the VD5 tunnel down around VD4, from the eastbound platform tunnel, and also from the advancing face. And that required enlargements to the face. You can't drill a well straight out of the face because it'll just be lost as the face gets broken out for the next advancement. And in section, this is what we had. So you can see the enlargement. So we had 2 intervention points that were identified and built into the design of the tunnel. And then we lowered the rig down the slope and drilled out into the tunnel. And because we were working progressively, and because we had the wells installed from the other tunnels, we were never having to deal with artesian pressures as we were drilling, which made life a lot easier. One of the piezometers survived in the shaft. It was very helpful to tell us what was going on. And we now have compact ejector pumping stations for use in the tunnel. So below the Lambeth Group, we have the Thanet Sand. And as I've said before, when we're considering the Thanet Sand, we're also thinking about the chalk because they're in hydraulic connection. This exposure is from the tideway shaft, tideway east at Chambers Wharf. Thanet Sand finds downwards typically, so the hydraulic link between the Thanet Sand and the chalk is not quite as good as one might think. So we're going to go back to the limo, the crossrail shafts there, and we're now going to look at the main drive shaft. So this was a 30-meter diameter shaft, 44 meters deep, had a 55-meter deep diaphragm wall, and this was the launch chamber for the 2 TBM drives towards central London. And in the long term, it became a ventilation shaft and emergency access shaft. So here we've got the ground profile. So the chalk is down at about 70 meters. So we've got a good thickness of London clay. We've got a clearly defined layer in the Lambeth Group of channel sands, and then we've got the Thanet Sand and the chalk. And the permeability of the chalk's about 10 times that of the Thanet Sand. So the diaphragm wall was installed initially. That provides a full cut-off to the River Terrace deposits. The shaft is then excavated down to full depth, and you need then full dewatering of the channel sands. But that's relatively easy because those are also fully cut off. But you need significant pressure relief in the Thanet Sand. Then you get the base slab installed, and you can reduce to some extent the amount of pressure that you need in the Thanet Sand. And we need, one of the things is to aim to minimize the pumping when that's going on. Once the TBM is complete, the slab is thickened and the roof is put on, and at that point you can turn all the dewatering off. There's no pumping needed in the permanent condition. So when we're excavating down to full depth, we were actually pumping from 7 chalk wells externally. We had 6 external Thanet wells, and we also had 6 internal Thanet wells, so 12 Thanet wells, and then we've got the passive relief wells in the sand layer, but because it was cut off in this case, there was only 3 of them, and that's very low flow. So in plan, you can see the auxiliary shaft on the right we spoke about previously had the passive Lambeth Group wells in it. That was all. The drive shaft, just a couple of relief wells because this is cut off. And then we've got internal and external Thanet wells close to the shaft because they only have a very local effect. The chalk wells have a much wider influence. They're not necessary. They don't necessarily need to be so close. So they spaced further back where it's more convenient and where there's less interaction. Once the base slab was in, then the pressures in the chalk could actually recover back up to their original level, but we still needed some pressure relief in the Thanet Sand. So the chalk wells were actually shut down, the external Thanet wells were shut down, and the internal Thanet wells were just operated to drain passively, and that provided sufficient pressure relief. So if we look at that data on a graph, here we've got the data over about an 18-month period, 2011, 2012. The chalk pressures are in green, and the Thanet pressures or water levels are in red on the left-hand scale. And then on the right-hand scale, we've got the flows. Dark blue is the chalk flow, and quite high flows, and the Thanet flow much lower. And if we look at this, essentially we've got three phases of pumping. At the beginning, we're only pumping on the chalk at quite high flow, up to 160 litres per second, and you can see the chalk goes down and the Thanet drains down with it. Then, after a period, we turn on the Thanet wells, only pump an extra 10 litres per second, but you can see we get an extra drawdown, something like an extra 10 metres of drawdown from that. And you might think, well, why didn't we do all the pumping with Thanet wells? But this was 12 Thanet wells. We would have needed a huge number of Thanet wells in order to achieve that. Then once the slab was in, after about something, I think about 9-10 months, the chalk was turned off, the flows dropped to 10 litres per second just from the Thanet. The water level in the chalk recovered pretty much back to original level, and the Thanet level recovers, but it's down about 10 metres, enough for the remainder of the tunnelling period until the shaft can be completed. So this is a good illustration of how the Thanet and the chalk behave, in how they interact, and what different strategies you can use. So you need to pump from the chalk if you need a lot of drawdown, but if you need a small drawdown, you may only need to pump from the Thanet. So we're now going to look at Tideway, Kirtland Street. And this is a cautionary tale about groundwater source protection zones. So the shaft is located within a groundwater source protection zone, and that's because there's a major public water supply from the chalk wells, big chalk well, licensed to pump 80 litres per second, with an operating flow of about 60 litres per second. The shaft itself had a deep diaphragm wall that went down into the chalk and effectively cut it off. Very little pumping needed for that, no concern. The adits were constructed actually in the Lambeth Group, but close enough to the Thanet Sand to require some pressure relief in the Thanet Sand. So on section, here we're talking about tunnel datum, so ground level is probably about 105. Standing groundwater level 87, we needed to lower it by just over 10 metres, something like 12 metres, to keep the pressure down whilst the adits were constructed. So essentially just relieving the pressure on that Lambeth Group at invert. So the target only applies to the Thanet Sand. There's actually no requirement for dewatering in the chalk. Now, the water supply well hadn't been used for 3 years, but it was actually turned on just as the dewatering was required for the shaft. And when it was turned on, it actually achieved enough drawdown for the shaft. So, or sorry, not for the shaft, for the adits. So you can see there over time, there's the Thanet Sand, there's the chalk at the shaft and the chalk at the site boundary. And then the flow. The flow is the flow that we were pumping, which for a lot of the time was almost zero. But you can see every now and again it jumps up. And it jumps up because the public water supply well didn't pump continuously. They every now and again they didn't need it and they turned it off for a few hours. And when they turned it off, water levels bounced up. So we needed a fully fledged dewatering system, but we in fact could only turn it on when they stopped pumping, and they wouldn't tell us when that would be. So we had a monitoring system and a variable speed drive, and it was all automated. So that as soon as we saw the water levels rising in the chalk at the south side boundary, our pumps started to kick in progressively, and as soon as the water levels started to fall, uh, they they cut back, and that worked well. You can see there on at this point we pumped for quite an extended period, and that was because on Christmas Eve their pump failed. And it was a big pump. It took them about 3 months to replace it. So we were running entirely reliant on us for that period. So we tend to think of these source protection zones where we're having to protect the public water supply. In this case, we needed a whole system to protect us from what they were doing. And finally, we get to the chalk. And we're just going to look at excavations which reach into the chalk. So the photo on the left is a CCTV picture of a chalk well borehole. So you can see it's unlined. We case it down into the chalk and then drill unlined. Because it's rock, it stays open. We can just see a flint band there. And then on the right, with the camera, we can get a sidewall view, and we can see a little water-bearing joint that feeds water into that. Much of my early experience with chalk was at outcrop outside London, like this scheme in Newbury. Here, the chalk has been subject to periglacial weathering, often to significant depth, rendering it relatively heavily fractured and quite soil-like in terms of its sort of behaviour, in terms of its instability, and permeability is sort of relatively uniform. And you can see it's soft enough that we have to use lined wells. We can't use unlined wells. That is markedly different from the chalk under the London clay in central London, because it hasn't been subject to periglacial weathering. So it's hard chalk. You can core it. It stands in wells, as we've seen. It's typically pretty anisotropic because the chalk matrix is really not very permeable. All the flow is in the fissures. So the vertical permeability, if a lot of the fissures are horizontal, can be much, much lower, certainly 2 and possibly 3 or more order of magnitude lower. And the flow is subject to how much jointing there is. And the jointing is subject to the overburden stress. So when you've got more than about 90 meters of overburden, it seems the joints are pretty shut and you get very little water out of it. But at shallower level, there's been quite a lot of stress relief due to the erosion of the soil above. So the fissures open. Chalk is soluble, so once water starts to flow through the joints, they may open over geological time. And if you've got valleys and things like that, then you may get structural features and quite a lot of faulting and permeability. So this is the kind of strategy that's adopted. This is, again, Deptford Church Street. This is the deep structure there. This is in East London, but this strategy has been used in many parts of London. And what we do is we install a test well to begin with, and we do a little pumping test on it. We run geophysics on it. Then we review how deep the diaphragm wall needs to go. and consider whether any sort of grouting options might be required to reduce the inflows. Then install the diaphragm wall. Typically, we might then install a second well and repeat the pump test, pump on well, monitor in the other, and just confirm that the inflow is low. In this case, they needed the flow to be low because they only had a limited discharge capacity. And the second well also means provided some pressure relief to make sure you haven't got a heave issue due to the sort of anisotropic conditions in the chalk. And then there are contingency measures. So one contingency measure would be to extend the depth of the D wall, grout curtain below the D wall, or base grouting. You have to think about uplift pressure for that. Chalk wells, we typically develop them by acidization. So we drill the well, we clean it out, and then we put in a quantity of concentrated hydrochloric acid. That generates a lot of gas, so it needs to be done with great care. We pressurize the well, but it does a great job of cleaning the well, of improving the well yields, and also giving us a very good view of the wall of the borehole when we put cameras down. And one of the very useful things that we do now is we undertake geophysical logging of the wells. So that's a typical well, case through the overburden, and then open hole in the chalk. And we can run a thing called a fluid log through the open hole section. We actually can see there, first of all, a caliper log. So this is a 200 millimeter borehole. You can see the casing is 200 millimeters, then it opens out slightly below the casing, probably a bit of overbreak, and perhaps as a result of the acidization, but it tapers down to about 200 mil at the base. We run conductivity and temperature logs, and you can see those are pretty steady, although there's a bit of a kick in the conductivity log at depth. But the key thing we look at is the fluid log. So we put a pump in the well, we put a flow meter down the well, and we monitor the uphole velocity in the well. And that tells us where the flow is entering the well. And typically we see the flow entering towards the top of the chalk, perhaps the top 50 to 20 meters. And usually in this case, relatively little was entering the well, apart from at 66 meters depth, virtually all the inflow came in. And in this case, it was about 12 litres per second. And that was about 4 meters below the bottom of the diaphragm wall. So great concern here that that would lead to too much flow coming into the shaft, because for the 12 litres per second, we were actually getting relatively little drawdown in the well. In practice, this was investigated, and it was proved that the fissure was there with a couple of other wells, and then the grouting was carried in the wells, and that succeeded in reducing the flow without the need for curtain grouting or base grouting. So there we are into the chalk, which for the moment, as far as we go, or certainly I've been, in the London Basin. This picture shows one of the shafts for the London 2012 cable tunnels. And this was actually the first time that I'd been involved in a shaft where we used all three of the sort of main techniques we use. So we had deep wells providing the pressure relief or the dewatering in the chalk. We had ejector wells dealing with the channel sands in the Lambeth Group, and then the Thanet Sand did not fully drain with the chalk, and we had 2 stages of well points that you can just see down the bottom there. So you can see they're just removing the last bit of the Thanet sand, and then the surface of the chalk is just being exposed. So I hope that I've given you some idea of the range of dewatering strategies on offer for groundwater control in the London Basin. Thank you.
I think you certainly have. Thank you very much for that. I think let's move across to have a look at if we've got any questions that have come in. Okay, well, I think whilst we're working our way across to look at any questions coming in, if I could ask you to put any questions that you've got for Toby in the chat. But what I've got a couple of questions for you whilst we're waiting for the technology to come through. What would you deem as your most complex challenge to date? You've showed us such a variety of projects. What would you, if you could pinpoint one that you look back on and you think that was probably one of the most complex ones, what would you say it would be?
Well, that's tricky. I mean, actually, it's the work we've been doing in Toronto, which
They picked us.
has a lot of similarities to London. The soil in Toronto is very like the Thanet Sand, but there's a lot more of it, and there's no handy chalk layer to underdrain it.
So that slight change in the geology stratas makes the difference.
Makes a big difference, and also it's all much shallower. So they were building stations with SCL in that material,
Right.
and we were having to fully drain it down to interfaces, and it was fascinating and challenging.
Yeah. So more the overall combination. So imagine Toronto didn't exist. What would be your number one challenge here in the UK
I think the
or
work
in
that's
London?
been the work I haven't mentioned it, but the work that's been going on at Blackfriars
Okay.
on Tideway, where we had everything going on. They were sinking an SCL shaft in the river at depth onto an existing TBM that was just about that they were founding, in the Thanet Sand, quite close to the chalk. Very substantial drawdowns.
Yeah, definitely the big challenge is Blackfriars. Yeah. So you also mentioned over the last 30 years, sort of quite a bit of difference in technology and equipment that could go underground. Other than equipment, what else would you say has been the biggest change in dewatering over the last 30 years?
Oh, and there's no doubt that I know this partly because Martin Preen's book on dewatering. I've written the last chapter for it, which is called The Future, and it's now on its 3rd edition. So I've written it 3 times. So I've looked into the future and then lived it. The Syria guide has also been updated, and I mean the biggest change when we updated the Syria guide is the environmental world that we live in.
Mm,
When I first started, you basically designed the dewatering, installed it, you went to site and started looking for the nearest manhole to shove the discharge down.
mm.
And obviously, it is a very different world now, quite rightly.
Yes, it is.
But understanding, those there's an absolutely major driver now to what we do, and understanding all of that is vital.
Yeah. I think also very interesting what you were talking about the ground protection zones and actually what you learned about being mindful of it being used in a different way. I think that must have been quite a surprise knowing when they turned their system off as to probably not something you were expecting to be happening and providing you with different challenges as normally it's about getting the consent to be able to work alongside, but not thinking about the situation being slightly different to what you were planning for. So yeah,
Yes.
quite an
No,
interesting things to be mindful of.
yeah, no, there was a lot of discussions around that. And it had been off for some years, so it was quite a surprise when they said, well, we're actually about to turn it on.
So, what do you want to do that for? So another one then, I think you sort of slightly touched on it, but what do you predict for the next 30 years? Where can we're on to version 3 of the future. What would you be putting into version 4 is probably where you sort of pipped me on the question.
I mean, what we're going to move into is a sort of carbon world, and that is happening now. And I think that because dewatering doesn't use a lot of steel and doesn't use a lot of concrete, it actually has relatively low carbon footprint
Yeah.
if compared to other things. And I think that penny is beginning to drop with people. And as they start withdrawing the temporary works, or
Yeah.
particularly the concrete that we leave in the ground for temporary works, withdrawing that, then you start looking at, oh, I actually need a bit more dewatering.
Yeah. So I think it's quite an interesting thought, actually.
Mm,
There's a lot of work with the carbon agenda at the moment, so I think definitely we need to keep following up and seeing where you get to with that.
mm.
Most definitely. So I've got one other. Um, maybe I might slightly rephrase it, but I was going to ask something about what 3 things do you wish construction projects would learn from? You mentioned sort of like the comments about where people didn't realise that with passive release wells that they were going to get water. What other things would you wish that projects would learn and know about dewatering and
Oh, well, the sort of biggest current issue is the environmental permissions. It changed in, I think, the 1st of January 2017, um, without much announcement, and the industry has been pretty slow, really, to catch up on it and to understand that you need, if you're going to be doing any serious dewatering, you need to be thinking about that a year in advance. And if you're not thinking about it in year in advance, it might drive your program.
yeah, okay,
And we've got quite a few projects where it is driving the program.
duly noted. So I think that Divix, we've got some questions up from those of you that are online this evening. So the first one I've got is from Medi. How do you compare the benefits of recharge you mentioned with disadvantages like potential treatment requirements, space requirements, especially in small sites, and environmental consent requirements?
I mean, you do recharge usually because you have to do it. If there's it costs money, so you wouldn't do it unless you had to do it. So to some extent, you have to make it work on with the constraints that you've got. And there have been all kinds of techniques for doing that, building treatment plants up in the air, um, so you can work underneath it. And I mean, the environmental consents, yeah, you need them. I mean, what's interesting about recharge is that there is an exemption for recharge. So if the water that you abstract, you recharge back into the same aquifer, regardless of flow, and providing there is no sort of other environmental concerns, like you're within a source protection zone or there's SSI nearby or something, it's exempt. So it doesn't need licensing. So that is quite a big plus.
Okay. We've got another one in from Claudio. Um, while dealing with contaminated ground and dewatering, what options would you consider and in what order of preference?
So contamination covers a lot of different things. I suppose we first of all tend to think about hydrocarbons because they're likely to be a problem wherever you put the water. And so then you're looking at sort of activated carbon treatment. And if you're pumping 10 litres per second, that's quite a small treatment plant. If you're pumping 100 litres per second, that is a big treatment plant and a big cost. So it all comes down to cost. What are the flows? What are the treatment costs? Is it cheaper to start physically trying to cut this stuff off, or is it cheaper to treat? And if the flows are high, it's probably cheaper to cut it off. And also, if it's contaminated and you're pumping it, are you spreading the contamination? So there's also real issues around permissions and consents.
There are a number of factors really to
Yeah.
take on board. So we've got one in next from Tunnel Talk. What is your opinion of the fear of surface settlement restricting or disallowing dewatering? Has the control and application of technology allayed those previous fears? And I think this question carries on, just looking at how it flows on YouTube. And what is your experience of using compensation grouting in combination with dewatering to counteract surface settlement in conjunction with shaft, tunnel, or cavern excavation? You might want to take that question in a few parts.
Few parts.
Yeah.
Okay, so the thing about settlement from dewatering is it's proportional to the drawdown. And the drawdown can be, if you're pumping from the chalk, it can be kilometres. And that's under draining the Thanet Sand. So it's very different typically from the settlement that you see from tunnelling or from a cavern, where the settlement is very local and you get quite significant differential settlements. Here we're talking about low differential settlements, and the principal concern is actually shallow structures linked to deep structures. The shallow structures will just simply go down a few millimeters and possibly go up a few millimeters at the end and aren't a concern. And on that basis, we can observe, I described the hydrostatic profile under London. London has been under drained from the chalk for 150 years. London is settling due to that pumping and has been, and it's quite a few millimeters a year, and we all seem to survive. So it's difficult to do compensation grouting because of the areas involved. It's much too big. It's really a question of assessment. I mean, the worst problems are if you're dewatering in the terrace gravel and under draining soft alluvium, and there you need recharge to maintain it. For deep dewatering in the London Basin, really you have to assess it and decide whether you can live with it. And if you can't live with it, then you can't dewater and you've got to do something else.
Okay. Next one we've got in is from Steve Parker. Really enjoyed the presentation. You talked about acid to increase yields. How far or what distance does this travel? Is it recovered or lost?
Hello, Steve. Good question. I mean, and we've looked at this quite closely. And the answer is not far. Because we're talking about typically, for most dewatering wells, sort of 1 or 2 tons of acid. So that's a couple of thousand litres. But when you start working out how far that might go into the ground, it's not that far, even though the porosity or the fissure porosity of the chalk is quite low. And of course, we also, it reacts with the chalk, so it's neutralized fairly quickly. And as soon as we've done it, we do clearance pumping and we pump it out. And of course, as soon as the well's installed, you stick a pump in it and you start pumping it like mad. So it's actually what the water supply people have done for decades.
So I think I'm just reading this next one. I think this may be very similar to one we've already had. How do you make a decision on balancing the settlement or subsidence issues versus dewatering induced settlement? And that's in from Trevor, I think. Unless there's anything else you want to add.
I mean, once you get below the top of the terrace gravels, you're dealing with soils that are pretty dense for the most part in the London Basin. And so the amount of settlement that you're generating is, in the time frames of a construction project, you wouldn't expect the pore pressures to change much in the London clay or the Lambeth Group clay. So essentially you're talking about, and the chalk is very, very stiff. That's not going to move at all. So you're really talking about consolidation of the sand layers. It'll occur virtually instantaneously with drawdown. So it happens once. And so you need to assess it. And the difficult thing there is actually measuring the low strain stiffness and getting measurement. And the best way from that is from case histories. And then it's really a question of looking at structures and saying, what might the concern be? But it's also worth bearing in mind that most of London has seen this very substantial drawdown, which went down and is now gone back up again and is going back down again. So it needs to be looked at and considered, but it's not immediately obvious why it's a major concern.
Yeah, that is quite a part for people to remember, really, and probably on the list of things that people need to have as a guide before you start a lot of your considerations. So I think that we have. I think that's the close of the questions that we've got. So I want to thank everyone firstly for the questions that they've put in the chat, but really want to thank you, Toby, for coming along this evening. It's been a really interesting and informative talk. Little bit jealous that Toronto has pipped us though with some of the biggest challenges. Someone needs to be coming up with some projects that give you some more challenges here to solve, because it sounds like you've solved a lot of challenges for UK projects. So yeah, thank you very much. I think some really interesting case studies. I think it's going to be interesting to see what happens over the next 30 plus years and see whether some of the work, particularly on things like sustainability, brings any changes, and whether there's some things from left field. I think lots and lots of work done with equipment that have really changed what we can do and how, but also understanding the real suite of those strategies. So thank you very much. It was extremely informative, and I know a lot of people will be using that as a very handy reference guide also for guiding their thoughts on what they do on their project. So thank you for your time. Really appreciated it this evening. So yeah, thank you. So I think, Divik, we've got a couple of announcements this evening. Just bear with us a few moments whilst we transition across the slides. Yes, if I could have the first slide, please, Divik. So we've reached September and the world is beginning to get a little bit back to normal. So the BTS have pipped the BTS to the first in-person event, and they have their first in-person social on the 29th of September. So feel free to join them. It's the evening before the BTS conference and it's at the Tattershall Castle. Next slide. So the next one then is just a reminder that the BTS conference takes place on September the 30th to October the 1st. And it's a 2-day programme, £160 for BTS members and 205 for non-members. So really looking forward to meeting as many people again in person. This will be our first in-person event, and really look forward to seeing you all there. And that's at the QE2 Conference Centre. Next slide. And really a reminder that the BTS will also, as well as the conference, will be holding an additional evening lecture. So you get a bit of a freebie in the calendar this year. And that is on closing the loop back analysis of sprayed concrete tunnel junctions. And that will start at 6 o'clock. But what I would ask is if you could pre-register so that you can attend, so that they're not having to put lots of people through at about 5:30. So please pre-register and really look forward to seeing you on that evening. Next slide. Then back to our more normal routine. However, really significant moment on the 14th of October, we have our first BTS evening lecture back at 1 Great George Street. So this will be my first meeting in person. I've been your chair now for about a year and just over a year. And this will be on low, intermediate, and high pressure compressed air work, the launch of the revised BTS CAUG guide. So, really looking forward to seeing as many of you as possible in person and hopefully a little bit more back to business as usual. Next slide. Next one then is to say that application for members are now open for the BTS Young Members Committee, and you need to apply by the 10th of October. The application link will go live tomorrow on the BTSYM's social media pages, so please check it out, and there is also a link in this slide as well. Next slide. A little part now on the progress of BTS at 50. As you know, we've got a suite of songs that we raised earlier this year. Next slide. And just as a little bit of an update on the BTS 50th anniversary book, bit of our target program. We, as you know, and I've been mentioning for many months now, we have been inundated with stories, and we want to make sure we get this right. It's been really interesting seeing some of the stories that have been shared with us. We will be showing some of our work for how we're progressing so far at the BTS conference on the 30th of September. And we will be opening a page on the BTS website for people to register for notifications for when pre-ordering commences. We're hoping to be open for pre-ordering before Christmas with a print in April 2022. But I can certainly assure you that when you get to read it, there's going to be a lot there. So yeah, fantastic piece of work. Couple of additional notifications. You don't need to register for notification of when pre-ordering commences if you are an author, a BTS member, or you registered for notification as a part of the survey in late 2020. You will already be automatically notified. And there we go. That's the end of my announcements for this evening. So welcome back. I hope you all had a lovely summer break and really look forward to seeing you in person very, very soon. Thank you and good night.